Hello, my name is Donovan Gray, and this is my lab report of Lab 2 charge tape revisited, where we look back at the charge tape experiment, except we use a virtual Python model to better estimate the charge on each tape as it's pulled from the table. So, introduction, the exact same experiment. It's about the charging of clear tape. We have a piece of tape on the table, and we put another piece of tape on it, and we rip it off really quickly, and then it acquires a charge, and we do it twice. So we put one tape on two pillars, and we take another tape, and we hold it close to that tape, and we see how far or how close we need to keep one tape to the other so that it hovers above it. And due to Newton's second law, we know that if the tape is not moving, that means that gravity and the electric force are balanced, and therefore we can calculate the charge on the piece of tape. And like I said, and a little bit of a preview, the estimated charge on one of the tapes was found to be 1.6 times 10 to the negative eighth coulombs in this experiment. And one of the biggest assumption that we make is that the charge is evenly distributed across the length of the tape when we rip it off the table to acquire it. So a little bit of context from lab 1, of course, we have the diagram, as you can see, tape A, tape B, and tape B is hovered above tape A. But we found we had a 0.01 meter distance between tape A and tape B when in equilibrium. And based on that, when we only calculated tape A and tape B as point charges, we assumed that they were point charges, we got a 4.9 times 10 to the negative ninth coulomb charge, or 4.9 nanocoulombs of charge on each piece of tape. And the major assumption we made then was that each piece of tape was a point charge. The new model is completely different. It treats, or it tries to estimate the pieces of tape as a series of individual point charges. And we're not, I mean, of course, we can't use integration because we can't take an infinite number of discrete charges, but we use a large number of discrete charges, and this better models what's actually happening between the two pieces of tape. The white arrow is the force of the lower tape on the upper tape, the electric force. Yellow arrow is the force of gravity on the upper tape. The green arrows are the electric fields on each point charge, dq, on the upper tape due to the electric field from the bottom tape. And the red dots represent the upper tape, and the blue dots represent the lower tape. The magnitude of the electric force on tape, on the upper tape, is 2.1 3529 times 10 to the negative third, and the magnitude of the gravitational force is basically the same thing, 2.1582 times 10 to the negative third, which makes sense. Like I said, Newton's law dictates that those two magnitudes should be balanced and pointing in opposite directions, which they are. Here's the glow script code. Based on that force we calculated, or that our model spat out, we were able to estimate the net charge to be 1.6 times 10 to the negative eighth coulombs. And then we have the E field function, which gives out an electric field based on a charged particle and an observation location, and the line charge function, which creates or generates a line of charges. And then here we are creating the top tape line charge and the bottom tape line charge, and there when it says n equals 20, that means that we are taking a discrete sum of 20 different charges. And in this code we denote them as dq, but they are discrete sums. And the E scale that we use to scale the arrows is 2 times 10 to the negative seventh, and we have the F, the force of the electric field scale, and the force of gravity scale as well to make the arrows more visible in the model. Here we are actually summing up the total electric field and the force of the gravitational field, or sorry, the force of the electric field on tape, on the upper tape, and then down there we have the FE arrow, which generates the arrow of the force of the electric field and the force of the gravitational field. So a bit of discussion. What if we modeled each of the tapes as a single point charge? Well, that was the entire basis of the previous lab. We assumed that each tape was a point charge, and we treated it as such. And we found that the charge in each tape was 4.9 times 10 to the negative ninth coulombs, or 4.9 nanocoulombs. And that is obviously different than the charge we found now. The charge we found now is 1.6 times 10 to the negative eighth coulombs, and that is a whole order of magnitude higher. So why does this differ? Well, that's because if you have a line of charge evenly distributed among the full line, then each piece of that line, each point charge that we had before, doesn't contribute a full vertical force on the point charge in the other tapes, right? If we have a point on the very end of the tape, most of the particles that it's exerting a force on the other piece of tape are in an x direction, right? They have an x component, and so that field will have an x component, and therefore the force isn't concentrated in the y direction, so you need more force to compensate for that, so you can eventually counteract gravity. Conclusion from the computational model, we concluded, like I said, that the tape gained around 1.6 times 10 to the negative 8th coulombs of charge. A couple sources of error include discretion deviating from infinite sum. Of course, it can't perfectly match, and then also improper measuring of displacement and the initial lengths.